Right, 2.7 is implicit differentiation, and that's made up of two words. Two words. The second word is differentiation, which means what? To differentiate, which means what? To make distinctions among different groups of people? In this class, it means to what? Take the derivative, right? Find the derivative. So we're going to be finding the derivative in this manner, implicit. Now, I think y'all know what implicit means, right? Because back in the day, maybe when y'all were young, y'all purchased CDs. And when you went to the store, it says warning, right? On that bottom right, it said warning, implicit lyrics. Warning, implicit. And then the label is too small for the words. Right? You got to be careful with those implicit lyric labels. Because you could infer something from the lyrics that the author and singer did not want you to interpret it as, right? Of course, those weren't the warning labels. The warning labels were, explicit lyrics. And of course, what does explicit mean? Yes, good. It doesn't mean naughty, unfortunately. It is tied to the naughtiness that took place on the record that was not so implied. It was actually kind of in-your-face naughtiness, and that's why they called it explicit. You could make an explicit math CD where it's like, do your homework, man! That's explicit, right? Because there's like no doubt, but that wouldn't really sell. That album wouldn't sell. Especially if that was the only song and that was the whole song. That would not be good. But you could say those were explicit lyrics because you said explicit was what? Out in the open. There's no ambiguity about it, right? There's no interpretation needed. It is just laid right out there in front of you. Implicit, on the other hand, is something that is the opposite. It's something that's implied. Yes, it's a tacit interpretation, right? Throwing some SAT words out for you. It's left open to interpretation. So what the heck does that have to do with calculus? Some of y'all, when you do math, maybe you do it implicitly, and you're just like, I hope he understands what I'm doing, right? That's not quite what it means. Let's look at this, and this will kind of be a segue into the lesson. These bullet points means this is important for the lesson. The dx, of course, is the verb. And it means take the derivative of what follows with respect to x. And the denominator then is your independent variable, which is going to be very important. So on the top bullet point, if you take the derivative of y with respect to x, you end up with dy dx. That's the noun. That's the same as y prime. On this hand, though, if you take the derivative with respect to x of x, we've been getting what this whole time? 1. The derivative of x with respect to x is 1. But here's why it's equal to 1. This is actually what we've been doing behind the scenes. It's dx dx. And of course, dx is the differential of x. You could treat it like an individual quantity. And what's anything divided by itself? 1. So that's why the derivative of x with respect to x is 1. Because dx dx is 1. Is dy dx 1? No. It's dy dx because x and y are different. Okay, so what's nice then is when we have an equation like y equals x squared. This is what we say is explicitly solved for y. Explicitly solved for y as a function of x. Bless you. That's what we mean by explicit. Okay? There is a y on one side and nothing but numbers and operational symbols and x's on the other side. There's no y's over there. So it would be something like this in general. If you can solve for y as a function of x, that is explicit. And those are the ones we've been working with this whole time. But there are times where you're not going to be able to solve the equation for y as a function of x. And what this chapter allows us to do, or this section, gives us a method for still finding the slope of the tangent line for the graphs of those equations that we can't solve explicitly for y as a function of x. Now let's see what that's going to look like. Here's a nice way to kind of show it and compare the two. This is an equation that we could take the derivative of right now. This would be an equation in explicit form. It's solved for y explicitly, no ambiguity, as a function of x. If you simply take that x in the denominator and multiply both sides by x, you get an equivalent equation that is now not explicitly solved for y as a function of x. This is what we would say is an implicit form. And they're the exact same equation everywhere except at 0. Of course, this one doesn't permit a 0 into its domain, whereas this one does. But everywhere besides 0, they're equivalent. Okay? They're both the same equation. We're going to learn in this section how to take the derivative of something that's like that. All right? So let's go ahead and do that right now. We'll compare. Example 1. Find the derivative dy dx of y equals 2 over x. The equation explicitly solved for y by taking the derivative of both sides. Now, what we've done in the past is we've rewritten it, and you would, I hope, would do that and not use the Hody-High rule. Yeah, you could use the Hody-High rule. And then from there, we would go straight to the answer, right? Let's go straight to the answer. What's the derivative of y with respect to x? Well, on the left side, remember there's two sides. So the left side would become y prime, or I'm going to use dy dx in this section. It's the same thing. It's Leibniz form. And the right side would become negative 2x to the negative second, negative 2th power. And then if you clean that up, of course, because we always like to clean things up, negative 2 over x squared. Nothing to it. Y prime or dy dx equals that. That's what we've been doing. Here's the reason I left the space. What we've actually been doing, and I mentioned this in the beginning, is we're taking the derivative of both sides with respect to x. That's essentially what's been the mechanism that has allowed it to work behind the scenes when we go straight from the blue line to the second blue line. And now on the left side, what becomes of the derivative of y with respect to x? It becomes dy dx, right? Now on the right side, of course, we're going to get the same thing, but here's a new way to think about it. If you put that x in parentheses, is that okay? Does that change the problem? No. You can now read that not as 2x to the negative first, but you can read it as 2 blob to the negative first. And do we know how to take the derivative of blobs? The derivative of 2 blob to the negative first will be negative 2 blob to the negative second, and then times the what rule? The chain rule, the derivative of x, because that's what's inside, with respect to x. That's what we've been doing. That's the chain rule. But why do we not need that there? What is dx dx? It's 1, right? That's what I said up here. Dx dx is 1. So that's why we haven't been writing it. Okay? But there is essentially a dx dx there. That's going to be important when we get to the implicit form. So we got dy dx equals negative 2 over x squared. And if I gave you this problem to still do, I would hope that you go just from one blue line to the next blue line to there and be done. But the mechanics of what we're actually doing here is important for the implicit portion, because that's what we're doing on example 2. We're going to do the same thing. We're going to take the derivative now of the same equation, but now it's in implicit form, xy equals 2. If it's in implicit form, you can't just go straight to dy dx equals, which kind of indicates the process that you're doing. So what we do then is we take the derivative of both sides with respect to x. And now that's indicating our method, which is super important to show. There's no dy dx going on at that moment. Now on the left side, notice we have an x times a y. That is a product of two variable functions, yes? Do we have a rule for such an occasion? The product rule, yeah. So let's go ahead and take the derivative using the product rule. The derivative of x, the first factor with respect to x, is dx dx. I'm going to go ahead and write it like that. Times the second factor goes along to the right. Plus x gets rewritten now times the derivative of the second factor, y, with respect to x. What's the derivative of y with respect to x? dy dx. So there's the product rule. Dx dxy plus x dy dx. Makes sense, right? And on the right side, what is the rate of change of any constant with respect to any variable? 0. 0. Now that's the calculus part. The calculus is over almost as quickly as it began. But if I want to get a derivative equation, I now need to do a little bit of algebra after the fact. I need to solve for dy dx. Now, of course, at this point, You don't need to write the dx. I'm going to go right now and say it's gone. It's 1. So to solve for dy dx, I'm going to leave it on the left side. And then I'm going to bring the y across and it becomes negative y. And if I divide through by x to solve, I get dy dx is negative y over x. Now, if I'm doing an equivalent method on an equivalent equation, I should get an equivalent answer, right? That makes sense. Let's compare what we got in example 1. Negative y over x is exactly not the same as negative 2 over x squared. Uh-oh. Or is it? It is. And I'll show you why if you can't see it. Notice that when we take the derivative implicitly, and that's what we did on example 2, it's called implicit differentiation because the equation is not explicitly solved for y. We had an x and y on one side. We ended up with both an x and y in our derivative. And that's usually the case. If you don't solve for y explicitly, expect to have y's in your final answer or x and y's. Now, if we wanted to show that they're the same, here's what we can do. On example 2, if we realize now, after the fact, that I could have just solved that for y to begin with by dividing through by x, it would be well worth it to look for that opportunity. When you're handed an equation and it's not explicitly solved for y, look to solve it for y first, because if you can do that, differentiating explicitly like we've been doing is going to be a lot faster, a lot cleaner. Your derivative is going to be a function of x. But if not, we can still salvage this. All I have to do is use substitution. If y is equal to 2 over x, let's plug it in right there for y, and I get negative 2 over x all over x, which, of course, if you simplify that, state change, flip, multiply by x over x, whatever you want, you get negative 2 over x squared. And that's the same thing that we got up there. So it does work. If you differentiate explicitly, you're going to get a derivative that's a function of x. It'll be a little bit cleaner, nicer, easier. If you differentiate implicitly, you're going to probably end up with both x and y in your answer. So look to solve first. You can't always solve for y as a function of x, which is why we're learning this method to begin with. A little note, though, about when implicit differentiation is needed. In this case, we could do it either way, which is why I started with this one, so we can compare and see that a method works. But in general, if you have an equation and it has x's and y's in it, and it's not explicitly solved for y, and you can't solve it for y, that means that it's probably not a function. It's not a function of x, at least, which means if you graphed it, it's not going to be a function. It's going to look more like this. And it might have a diamond there, maybe a diamond there. It probably has a circle there, parallelogram there, maybe a right triangle there. This is not a diamondback rattlesnake. This is just a snake that likes math and got some geometry tattoos and put some rubber bands around its tail. But this would not be a function, right? This would fail the vertical line test. But you know what? I might be interested still in knowing how fast this graph is changing right there. Right? Wouldn't you be interested? Yeah. So notice if you're just given an x value, is that enough to determine the slope at that point? No. If it's something that you can't solve for y, an x value is usually not enough, because if you just know the x value, you'd be like, do you want that one? Or do you want that one? Or do you want this one? Or do you want that one? Or do you want this one? Or do you want that one? Or do you want that one? Or do you want that one? How many tangent lines do we have at that x? More than one. Yeah, a lot. I lost track. So what does that mean? You're typically going to have to be given not just an x coordinate, but also a y coordinate, so that you can pinpoint exactly where on that graph, which is not a function of x, fails the vertical line test, where you are on that snake graph. Yeah. Look, that's like the Mona Lisa smile for snakes. All right. You ready to try it out? Blah, 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 left side, right side, blah, blah, blah. Let's go to example 3. Those words weren't important. They probably have errors in them anyway. Example 3. Find the equation, or for the equation, y plus equals, okay, I'm refocused. Good. For the equation y equals x plus, gotta be careful how you read that, right? That's secant of y. Secant of y. Not sexy. Y equals x plus secant of y. We want to find dy dx. Okay? Now you walk up to the problem and you're like, hey, look, it says y equals. Everyone look, y equals. That's pretty explicit right there, right? It's like, what is y? Y equals. It's right there. Pretty explicit, not ambiguous. Is that explicitly solved for y as a function of x? That's what it means in math. No. Because there's a what over there also? There's a y. Okay, so explicit means different things in different contexts. For math to be explicitly solved as a function of x, it has to be y equals again, and then no y's on the other side. Just x's and numbers and symbols. And in the recording industry, of course, explicit means, what do we say? Naughty. The first thing you want to ask yourself, though, before you just jump into implicit is, can we solve this for y? Because if we do a little bit of work on the front end, it's going to save a lot of work and possible grief and careless mistakes on the back end. Maybe is always a good answer, I guess. Well, let's see. To untrap this y from inside the secant, I'm going to have to somewhere along the line somehow take the inverse secant, right? And the inverse secant of secant of y will untrap that one. But if I take the inverse secant over there, I'm going to have to somehow take the inverse secant over here, which is going to do what to the y on the left? Trap it. So freeing one traps the other. Is that fair to the first one that was free? Who knows? Maybe they're into sharing the sentence. I don't know. But it's not going to help us solve for y. So you know what? No big deal. We have a method for finding the derivative without explicitly solving for y. It's called, you're implying what it's called. I like that. Read between the lines. It's called implicit differentiation. Yeah. The first step in implicit differentiation, which is what all these words are saying, blah, 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 is to show this, okay? Because there's no explicit way to show your method when it's implicit. So we're going to take the derivative with respect to x of both sides. Now, if you want to reshuffle some terms around just so that you have the y terms on one side to start with, that's kind of your prerogative, right? No one's going to tell you what to do. But you're going to have to shuffle terms around afterwards anyway, so whatever you want to do. Nothing needed to be rewritten in order to take the derivative. That's kind of the important thing. So we're taking the derivative with respect to x to both sides. Now notice what we're doing. We're not taking dy dx of both sides, are we? I see some students do this, and it shows a real lack of understanding. That's not dy dx of both sides because that's a noun. That would be like dy dx now times y. dy dx times that. We're not doing that. We got the verb going on, right? It's the derivative with respect to x on both sides. Okay, here we go on the left side. What is the derivative of y with respect to x? dy dx, right? Yeah, perfect. And on the right side, I have two terms. Yay, two terms. That's two problems in one. What's the derivative of x, the first term, with respect to x? 1, also known as dx dx. This is the last problem in which I'm going to do this. But yeah, it's kind of fun to write dx dx. Plus, now I'm walking up to secant of y, or secant of blob. What is the derivative of secant of blob? Secant blob, tangent blob, right? Secant blob, tangent of blob. And then times the what rule? Chain rule, the derivative of the blob, which is y, with respect to x. Okay? So notice what we did. We had two y's in our equation, right? How many dy dx's did we end up with? 2. Okay, so that's kind of a way to, for accounting purposes. Anything that is not your independent variable, and remember, Leibniz notation is nice because it preserves the independent variable. In this case, anything that's not an x, you're going to take the derivative like you normally would, and then by the chain rule, when you're done with that term, you're going to multiply by dy dx. Of course, if it's x, you don't need to put dx dx because it's 1. Yes, Tristan? Let's talk about y prime. When you show this right here, you got to show d dx. That's the verb. But if you want, you can call it y prime. I'm not going to, and this would be x prime. But that's kind of y prime is not illegal, and it is a lot faster. I like to use the dy dx's, as you'll see, because these types of problems are probably the most fun algebra that we're going to be doing all year long. And we're going to end up solving for dy dx a lot. And dy dx just stands out very prominently. And y prime can kind of get lost in a whole line of terms. And, of course, you can even mistake it for y to the first. You know, and especially if you put like that prime like way too far away, then it really loses all of its meaning entirely. But it's not wrong. When you get back from lunch, I'll show you how to do some algebra, because the calculus is over for this problem at least. But there's more to come. Fret not.